Hello, everybody. This is Kudan Open Lab Seminar, and it's not an April Fool's joke, even though we happen on April 1st, 2024, and it's Easter Monday. Today we have James Evans, who is the director of the Knowledge Lab and the Max Palevsky Professor in Sociology at the University of Chicago. And this is really amazing opportunity because there's very few people who sort of are all across the board of what cultural data analytics can be, should be. But James is definitely one of those, with a previous contribution suggesting embed everything, which of course we also believe in. And today he will talk about from simulated subjectivity to collective consciousness in large language models. We're all ears, and we're super happy to discuss with you about this really amazing topic. Thank you very much.
My pleasure. And I will say that whether it's an April Fool's joke or not will be determined over the course of the presentation. So I'm delighted to join your group today. I have I'll just walk through, please feel free to interrupt me throughout the presentation. I'll share some ideas, and then, but I encourage you to kind of just, pipe in throughout with specific questions, clarifying questions, or large scale, presentation level questions. And then I will also self-delimit my presentation with a gentle chime here. In Seattle, where I'm presenting from, and so that if you don't interrupt me, I will interrupt me, and I can hear from you, which is my great hope for this morning. So, my research lies at the intersection of broadly three areas. One is the science of science and innovation. Another is computational social science, and by this I don't mean using tools from data science to ask traditionally social scientific questions, but really taking imaginaries from computational science, from complexity to optimization to other powerful tropes and ideas. For example, the formalization of programs into computational social science as research opportunities and problems, and vice versa, taking sociological ideas like the structure and complex relationships between individuals in conversation into computer science, for example, to rethink and reimagine deep neural networks as social networks. And then the third is augmented AI, which is to say AI which is not the most human, but in some ways the least human, or AI that plays with humans and humanity, ideally designed in an engineering sense to complement human capacity rather than to replace it. But also, this requires us to understand more, not less, about individual and collective human, social, and cultural capacity. And so, for me, my work really is at the overlap between these classes of things, and I do a fair bit of convening. So, this last year and a half, I was involved with Erica Fuchs as the overall director, as the research director of this National Network for Critical Technology Assessment, mandated by Congress and the CHIPS and Science Act. And so I spent a lot of time building models of technology that would predict future tech and who was developing what where. I'll mention that briefly today. I'm running a Science of Science and Innovation conference at the National Academies of Science or National Academy of Sciences in DC, that is going to take place July 1st through 3rd. If anyone is interested, this is really an exciting gathering for us. But we're going to do a European version next year, probably in mid-June in Denmark. So I encourage those of you with interest to reach out to me and let me know, both to come and if you're interested more broadly to participate in organizing. And I've been involved in broader conversations that try to elevate questions of really a science of science. How do we build really scientific and technical and engineering insight into the process of funding and guiding science as a whole, especially as national budgets are shrinking and other concerns arise about the values to which science can be placed, my encouragement is that we build a really rich scientific, social scientific, and cultural and portfolio-based understanding of what science is as a broader project and how we can engage with it in such a way that we can maximize the values that we seek from it. I also ran IC2S2 a couple of years ago and actively attend. I think I'm doing some tutorials there this year. It's going to take place at the University of Pennsylvania this summer. I run a journal called Journal of Social Computing and a computational social science master's program. We just started a data science program here at the University of Chicago. And then I'm really interested, I would say, in some ways, a large part of what I do is focused on building complementary AI and understanding the complementarities that AI could produce. And so I run an annual conference called Plurality, which is really focused on kind of a Web3 based approach of thinking about designing systems that celebrate cultural pluralities, and also to build AIs that take seriously this idea of building cultural provocations and complements to complement and augment human capacity. And I just started a new initiative at our Data Science Institute focused on complementary intelligence that I'm directing with Chin Hao Tan, a computer scientist at the University of Chicago. And I spend a fair bit of time building kind of, I'll call them alien intelligences in the context of scientific development so that we can develop provocations. And so that's really the structure of the specific work that I do, and we'll talk about some aspects of this today in greater depth. So today I'm really going to talk about building large language models into digital doubles for social and cultural analysis. And what is a digital double? Well, a digital double is a data-driven generative model that allows us otherwise expensive and sometimes impossible capacity to observe, to interrogate, and to simulate social and cultural phenomena. And why would you develop a digital double? Well, because, or under circumstances in which you lack sufficient first principles models. And by sufficient, I mean models that can predict almost all of an outcome, that can produce in simulation almost all of an outcome. And so really the focus here is, and I would say this is true not just for social and cultural phenomena, but also for many natural phenomena. So that, for example, in chemistry, we might have a general understanding and really strong first principles models for how species of very specific and simple chemicals in non-complex chemical species environments behave and react with one another. But even there, complex gangly molecules like polymers, we don't have strong first principles models. And so even in those contexts, there's been massive benefit by building data-driven generative models and increasingly large language models and other deep neural network associated models to kind of integrate multiple forms of data over multiple timescales to maximize our likelihood of developing data-driven prediction. Today, I'm going to focus on large language model approaches, although I have a number of other works and other approaches that try the similar game or strategy. So the fact that we have large-scale data about how it is that society talks and thinks, or thinks out loud, or thinks to one another, allows us to build really rich large language models that facilitated simulation, and so facilitates what I'll call kind of a global observatory on the one hand about how it is that society talks and thinks about these things and how it talks and thinks in different ways, and also a virtual laboratory in which we can simulate changes in the world and see how it is that cultural systems and social systems will likely shift in result of these changes or interventions. So So large language models really, in some ways, are the result or the love child of word embeddings on the one hand, or generalization from specific word, discrete words to this idea of word embeddings. And the second part is the idea of the language model and the conditional language model, which I'll describe in a moment. So word embeddings are really this matrix factorization idea, that if you take a list of words, as I have here, and a set of columns corresponding to context, and these contexts could be large contexts. Initially, they were in latent semantic indexing in the late 90s. This was in 1999, for example, I believe that Google introduced the idea of latent semantic index searching. These contexts were quite large. They were the full web page, for example, or website. If you take this matrix, this word by context matrix, then you develop some low K factorization of this matrix such that you have an orthonormal projection of words to K dimensions and context to K dimensions. Then this K allows us to interrogate the relative semantic position of words and contexts. And so we can talk about relative distances of meanings and words from one another. And this building up of word vectors and context vectors facilitated a much more robust approach to the modeling of meaning and transformed the use of the language model and the accuracy of the language model above its use in the context of specific words in which it had been deployed before. This was most popularized in 2013 with the word-to-vec model, which had really two models under its hood, a CBO, or continuous bag of word model. On the one hand, where basically the context of a word, which could be very small, was able or used as a device to build an autoencoder, which is an approximation, in this case, a precise approximation of the matrix factorization approach that scales orders of magnitude in size. And the other is the skip-gram approach, where you basically take a set of pairwise word by context pairs and then use effectively a logistic regression to predict the relative likelihood that conditional on a word you would find another word in its context, again, of the same window size. The second prediction requires more data, but it also produces greater semantic accuracy. So the magic occurred, I would say, in 2016, 2017, when people applied the language model. And by language model, initially, we were basically building a probabilistic model which predicted the probability of word Y, T, based on the words that existed prior to it. This merged with the conditional language model, which basically said, hey, I'm going to predict YT as a function of the words that came before and of some input. And that input could be a language input. It could be a vision input. It could be a prompt of any type. It could be a vector input that doesn't correspond with either language or image. So the idea is, given some prompt, some invocation, and the words which were a resultant from that prompt, can I maximize the probability of the next word in question? Now, one of the discoveries that really improved this language model was the realization, which is in the equation at the bottom of the screen, that there was a non-identity between, for example, the argmax of the product of the probabilities, that conditional on the prompt and the last set of words, what the next word was going to be, and the product of the argmax of the probabilities of those next words, which is to say there was a garden pathing problem. So the maximum or the most likely sentence was different often from the most likely maximum probability of the next words in a particular sentence. So for example, here we have a sentence: the news media is the most, important institution for democracy, in a self-aggrandizing Western sentence. So the idea is here, can we use something like beam search, which is the way in which this was initially done, where you would just actually trace out more branches of the whole sentence to predict and assess the probabilistic probabilities, or do an approximation of this, which is what large language models do today, transformer-based models do today, insofar as they do top N, so they're maximizing the likelihood of any particular next word, but they run through, in what we call multi-headed attention, many of these pathways at the same time, and maximize the likelihood of the overall prediction or sentence in question. So the structure of self-attention inside transformers, which are the basis of modern large language models, can be represented in this way. This is a simple graphic, or not a simple graphic, but it's a graphic that tries to capture some of the complexities of the self-attention mechanism. So the idea is we've got text like that at the top. News media is the most important institution for democracy. We have input embeddings, which correspond for all intents and purposes to the embeddings that we described earlier, that are capturing vectors of meaning. And these are vectors of contextual meaning. So they're meanings of words conditional on rich context. And with enough documentary background that these themselves, even though they're acontextual, already produce positions that really correspond deeply to capture syntax and semantics of words in question. Then we use basically kind of two vector weight models to produce a set of queries and keys out of these embeddings that facilitate the following task that we see in the left-hand side. So for word Q, or for the query word in the sentence, what is the most related word K? As the keywords or keys of the sentence. So in this case, so we're kind of building this database idea of queries, keys, and values. So if we take news as the query sentence, then we can see in this vector space, which is produced as a result from the scalar multiplication of the query vectors and the key vectors, we can see that news is closest in the kind of the cosine space, or the inner product space, which is the space that's being produced here, to the vectors for the words institution and media, right? So when we think of news, it's close to media, it's close to institution. It's somewhat close, but further from democracy, further still from is and for, from important, from news itself, from most, right? And so what's going on in this layer is it's basically saying, hey, in the long context window, and this context window could be thousands of characters, tens of thousands of characters. The new Gemini model has 1 million, not in characters, but on tokens associated with this that facilitates this calculation across 1 million characters wide. I mean, most windows, context windows, are smaller in the zone of thousands to tens of thousands. And then we take, after we do this assessment, we push the results through a softmax scaling, which is just a generalization of the sigmoid, to turn them into probabilities. And then we've got these probabilities. So the probability conditional on news that basically institution and media are highly predictive of the meaning of news in this context. And then we rescale those results through this set of values weights, which really pull right out of the input embeddings into a structure that's similar to the query and keyword structure, and produces a set of output embeddings that can be then input into the next level of the self-attention structure. So the overall structure involves, for example, for GPT-3, which was documented, 96 of these decoder levels, which involve feed-forward networks atop the self-attention mechanism that I just described, right? So 96 of those, and then 96 pathways through those. So you've got this, the news media is the most important institution for, whatever. And then you've got a positional encoding, which is in fact a random encoding. Sometimes it's, it's just a sigmoidal function right here. This is the sine wave. And then you basically send that through this stack of decoders In GPT-3, that was 96 times, right? So there are 96 multi-heads, which maximize the likelihood of this top P next prediction. At the bottom of this, you get this output vector after 96 levels, which assesses through the token embedding space the maximum P probability, in this case 4, for the news media is the most important institution, 4. So it gives this prediction of an output probability, and then moves on as a process to the next question. Now, what does it mean then to prompt these language models? And the reason why I would say they've really become much more powerful predictors of social and cultural phenomena is that if you look into, so there's several recent papers in the last year and a half that suggest that the inference process is in fact a powerful optimization. So this paper on transformers learning context by gradient descent, which was performed by engineers inside Google Research Cerebra team. They basically showed that if we have a transformer and a deep neural network, that the correspondence between the layers of the transformer that we just showed before and the steps in gradient descent of the deep neural network model correspond precisely in minimizing the loss associated with producing an answer to a question, producing a response to a question. So what does that mean? That means that basically these large language models have produced a cultural surface, a high-dimensional cultural surface in which, in response to a particular question, it's doing forward gradient descent. So it's looking at the minimum loss or the minimum error point that would produce the response of a given type in a given context. And so that's the game that we're going to be playing here. We're going to be producing cultural responses to cultural provocations, and we'll be exploring the degree to which they correspond to cultural simulacra of individuals, of higher level cultural entities and structures. So this is just a deeper analysis of this across context that really shows this tight association between gradient descent, which is really effectively being done here, but not through backpropagation. The surface has already been learned through forward learning and inference. Okay, so this is an example. This is not by myself, by a student of mine, Jinsol Kim, and his colleague at NYU in sociology, Byung-Kyu Lee, where they build deep learning model LLMs as simulated subjects to predict future attitudes. So you can see 3 different tasks here. A missing data imputation, where they just randomly mask different opinions by individuals at different time points. And then retrodiction, where they basically, pull out classes of questions that may not have been asked at a given time and try to predict those. And finally, zero-shot prediction. So these are questions that have never been posed before, questions from the future. And we've basically just encoded the cultural positions of people as a function of their position in the past. And so the model architecture is below. So they take an Alpaca 7B model, which is a derivative of the Llama 2 architecture that produces a semantic embedding. They also begin with a randomized individual belief embedding and a period embedding. And then they connect them through cross layers in a feed-forward neural network and dense layers that then facilitate their prediction of these questions that either were masked or that have never been posed before. And you can see that the predictions are really quite powerful based on this relatively simple architecture. So the missing data imputation is on the order of an R of 0.99. The retrodiction is on the order of 0.98. And zero-shot prediction, where you're bringing completely new ideas to subjects, is at R 0.67. So still substantial signal to information and opinions about completely new things. I'll give you an example from another research paper that I'm finishing right now with Hyung-Koo Lee and Austin Kozlowski. So here we just take a large language model and we pose it a series of prompting questions. So we give it a partisan priming. I'm a strong conservative and a lifelong Republican. In 2016, I was very proud to vote for Donald Trump, and I think the Democrats have been a disaster for this country. Or a liberal priming, right? I'm a strong liberal and lifelong Republican. In 2016, I was proud to vote for Hillary Clinton, and I think the Republicans have been a disaster for this country. So what's interesting about this is that we can, of course, alter and perturb these prompts as we do to make sure that the simulated respondent isn't responding to what in the psychometrics literature we might call a dog whistle. So, are people systematically responding, or in this case, are these digital doubles responding this specific way? So after the partisan priming, after the I'm a strong conservative, we give it a little COVID context. So this model was trained in 2019, before the COVID crisis had really emerged. This is in November 2019. It didn't know anything about COVID. Lately, one of the biggest political issues has been the COVID-19 pandemic caused by the new coronavirus. There's a lot of controversy about whether students should be required to receive the COVID-19 vaccine before returning to school. I think that a required vaccine is and then we allow it to complete. A bad idea, a good idea, but I worry about the possible negative effects of the vaccine. It's a violation of their civil liberties. It's a good idea not be working hard to make sure that my representatives in Congress follow blah, blah, blah. And then we take a GPT encoder and we take simply its own assessment of a bad idea versus a good idea. So we just tell it, what's the vector for a bad idea? What's the vector for a good idea? We subtract the good idea from the bad idea, and then we take the cosine distance between that derived vector and each of these positions. So it self-codes, that terrible idea, bad move, violation of the First Amendment are bad ideas, and that strategic moves, great plans, and smart ideas are good ideas in its own space. So we just allow it to give it a self-definition of those things with respect to its own evaluation. And then we see the degree to which this corresponds with how it is that Republicans and Democrats responded to COVID measures circa March 2020, when once those measures had arisen. And so what we're trying to basically see is, to what degree do we or can we produce a kind of a social simulacra or a digital double of Republicans and Democrats in these contexts that will respond to cultural events like the COVID vaccination and required vaccinations, right? Or other things, right? You can see all of the various, vaccine mandates, lockdowns, mask mandates, border closings, whether or not they trust institutions like the Center for Disease Control in the US. And what we see is a correspondence of about 0.86. So about 86% of these assessments are correct. So for example, as you can see here, Republicans are more likely to prefer border closings because they're more likely to prefer border closings anyway. They're more likely to prefer ending mandates of any type, vaccination, lockdowns, mask mandates, trusting institutions like the CSC, or the requirement to trust those institutions. And what's interesting, I would say further, is that it is when these models are wrong, in the, say, 14% of the time when we don't get an answer that corresponds with the right outcome, in almost all those cases, history mattered, which is to say Donald Trump or liberals in the US took a position that was unexpected culturally, which causally changed the flow of cultural expectations. So when these models are successful, they're interesting. When they're unsuccessful, they're even more interesting because they actually point to, and this design can elicit basically causal estimates of historical phenomena that change the flow of cultural expectation out of its course. So in related work with LeCun Cao from my lab, we've really focused on how can we basically identify deep geometric perspectives in the context of these large language model surfaces, these cultural surfaces that I described earlier. This is work in which we situate individuals. So these PA, PB, PC, and PDs are individuals that have been encoded inside these spaces as a function of their prior work. So there are many such spaces. So we create basically an overtime evolution of science on the one hand, in which we project technology, of business discourse, in which we project new business plans and business descriptions for entrepreneurial businesses, about which we have very little other information. We build surfaces of novels and cultural phenomena. We project in screenplays that individuals write. We basically build up spaces of Wikipedia, and then we project in individual contributions in those spaces. And we find systematically that we're able to predict individuals' likelihood of combining two words or two ideas that are moving towards one another as a function of their angle with respect to those two things. So we have a deep geometry of perspective. It's much more likely they're going to be combining two ideas that they are, for example, PE here at 180 degrees of. So they're literally in the line of fire as those two ideas are coming towards each other. Than they are for being PA, who is equidistant to those two ideas, but is kind of cosmologically in line with them, right? So they literally cannot see those two ideas coming towards one another. And so we find the same is true for word adoption. If we think of one of those two circular points as the person themselves, if the word is approaching, the likelihood that they will adopt the word is precisely proportional to the visual angle, right? And the distance of the shrinkage between that person and the object in question. And the same is true in the converse of word abandonment. So if you take this across individuals, you can see that as ideas in general are coming together in the space collectively, it dramatically improves the likelihood that that will result in new generations, which is to say, by individuals in the space producing science or technology or Wikipedia articles or new companies or screenplays, which lie at the confluence of those spots, and far fewer as ideas are moving apart. Now, this is not just a tautology, because this accounts for the fact that none of these words themselves are being combined that bring the ideas together. So it's like a plate tectonics with individual kind of geometric predictors of individuals. Those positions, those geometric predictions, predict a view, a perspective, which then is highly predictive of output. And we can assemble those together, for example, to identify what about the relationship between individual perspectives and cultural products. So here we're positioning people as a function of their prior work inside this manifold of a culture space. And then we're assessing the degree to which the cultural products that they produce, so the screenplays, the new companies, the patents, the scientific papers, the Wikipedia articles, et cetera. I mean, we study bills that Congress people produce in parliaments and Congresses. In all these cases, we find systematically that the success of the product ends up being proportional to three things. One, the angle of individuals with respect to that thing based on their prior experiences, the lack of distance between those individuals, and the size, the positive distance of those individuals in the past, if we have more than one tracing over time, which is to say, basically, people from different perspectives, if they converge towards one another with a high degree of angle with respect to the object in question, is highly predictive. In fact, the most predictive ex ante factor with respect to success. By success, what do I mean? I mean citations in the context of research papers and patents, first weekend box office returns with respect to a consummated screenplay, something that actually goes into making a film, the average probability of achieving IPO for new ventures, et cetera, right? So there's a deep relationship not only between individuals and cultural outcomes, but also between basically the diversity of individuals and the success of a cultural product. And we're working now in the context of two things, both a Wikipedia experiment where we not only observe these from large-scale data, but we set out to test them to avoid any possible selection effect that shakes out into the observations that we see. So how can we recruit specific individuals from the Wikipedia space such that we achieve varying levels of diversity and their relationship to the success of the pages? I'm also working with Suna Lehman, which I'm sure many of you are aware of, to design an experiment. He and his team produced this very interesting Life-to-Vec paper in Nature Computational Science. And the idea is, can we specifically recruit individuals as a function of the information exposures to engage in cultural production activities that allow us to test this, accounting for the selection effect of the observed environment. Now, if you have not only closed models like, say, GPT-3 or GPT-4, with GPT-4, we don't even know the number of multi-heads. We don't know the number of layers. We have a number of parameters, and there's about 1.7 trillion parameters. Larger models are on the way. And of course, we know also now that there are like the Mistral models, like multiple 7 or 70 billion models, 8 in the case of Mistral, can perform basically at similar levels of performance to massive models. And so that's really a pathway to the future. But if you have access to the full model itself, we can find that just having the output vectors, we can do better by looking inside or doing kind of neuroscience on the system itself. So this beautiful paper by Roy Hendel, Moore, Giva, and Amir Globerson basically shows that in-context learning creates task vectors. So in this case, we can basically say, hey, apple is red, lime is green, corn is what? Well, yellow in this case. But we can find that this task vector theta inside the space of like corn, and then the arrow, right, is the operator that says, corn is, some color. That task vector is the thing that predicts the likelihood of that yellow, right? And so what we show here, what I'll show here, is that you can do the same for in-context personas or perspectives. So I can say, for example, the perspective of a Democrat is X, or the perspective of an artist with this experience is Y, or the perspective of a physicist who's written these 15 papers is Z. And then I can basically acquire this theta from the inside of the model in ways that are highly predictive, much more predictive than just the output vector at getting the perspective, for example, of that person or that persona, that simulacra of an individual on any particular thing. So this paper shows, and we've cross-demonstrated, that the average accuracy by layer, for example, it maximizes around 15 or 20%, which is about a quarter of the way through the structure of the network as a whole, a third to a quarter, right? So if you extract that, this is in the Llama 30 billion model to the 7 billion model, but it's actually quite stable. It creeps up just a little bit. And so here I'll give you an example of a simulated persona in the context of this task. I say, write an interesting idea for research paper. Assume that you're a sociologist, psychologist, linguist, philosopher, engineer, physicist, computer scientist, mathematician. And basically, we can see that the computer scientist is much more likely to be able to discriminate the difference between an interesting and non-interesting mathematics paper than, in this case, a sociologist or a psychologist are, right? They're just in very different positions in the space, right? I can do the same thing with respect to those political personas that I described earlier, right? So I say, from now on, assume that you're a Republican. From now on, assume that you're a Democrat, right? And so I can then basically extract this data and use that position as a generative position, which is to say, it can generate a perspective from that individual prompt that captures the relative likelihood of that view. So for example, here, I basically take the theta for Republican minus the theta for Democrat, and then I basically project every word of an essay about abortion highly contentious US political topic. And this is the native separation of effectively morphemes in the context of an English language sentence in a large language model. So as you can see, abortion is a highly controversial and sensitive topic. And we see, this is kind of trending liberal or Democrat in this context. Although when it talks about pro-choice and pro-life, those languages end up being more conservative. And then we can see the most fundamental conflict surrounds the right to choose versus the right to life. Pro-choice advocates believe that a woman has the right to control her own body, make decisions about her reproductive health, including assessing safe and legal abortion. Pro-life advocates, on the other hand, believe that every human life has inherent value and that abortion is taking of an innocent life. So it's able to very sensitively capture the relative position associated with each word as being generated from the voice of, in this case, a US Republican or Democrat. So I'm going to suggest that we can use these kinds of models to not only predict individual personas, but also fully cultural worlds. And I'll begin with an analysis or discussion of how it is that one can encode languages as a whole and understand how it is that meanings are organized as entire systems from the perspective of these language models. I'll take two cases which correspond to a paper that came out just a couple of months ago in PNAS with myself and Molly Lewis and the team at ETS, which is a major testing service in the US that allowed us generous access to their data. And a second with Pete Acebes, or led by Pete Acebes, which is really about the topological structure of different languages in context, just to give you a sense of how it is that these kinds of models facilitate that analysis. So the initial prompt came from my own linguistic anthropological background and the idea of the Whorfian hypothesis, the Sapir-Whorf hypothesis, which is really just that languages structure the encoding of meaning such that it shapes the reality that individuals see. I would say this was widely appreciated and then discredited in its hard form. So languages are Turing complete. People can compute any meanings in any reasonable natural language. But what has emerged much more recently from the late 1990s through the present is that it's much faster and much more cognitively available for certain meanings to arise as a function of the structure of language in some languages than others, right? And so what we're going to do is we're going to embed in language models both Wikipedia articles corresponding to each of the Wikipedias in this list of languages, and also the English language essays by people whose native language is each of these languages. So we're going to try to assess the relative similarity and position of a broad perspective and association of multiple meanings in English language essays by people who share a kind of language worldview and that language worldview within native language assessments of cultural phenomena in Wikipedias from that language. And we'll see is that this actually, we can perform this analysis on even just exclusively high-scoring essays. So these are essays that feel like natural and native English language. These are not just erroneous essays, right, with distinctive, let's say, Chinese or Arabic or Telugu errors, right? So these are high-performance essays that nevertheless retain these rich cultural traces. And so this is our assessment in the context of content that facilitates this analysis. So initially, we're going to look at the difference between the use of concrete and abstract words across these contexts with the intuition that basically abstract words are going to have a far different semantic position with respect to each other than concrete words across the space of languages. And then we're going to dive deeper into the structure of languages itself that are revealed by these language modeled proximities. So we find, for example, that semantic clusters actually correspond with concreteness deciles which is to say that that clusters of words end up themselves having a concreteness which varies widely across these language contexts in both multilingual Wikipedia contexts and also the English second language corpus. And we do find systematically that as words are less concrete, then the cross-linguistic word distance, the correlation of those distances is much further across languages. And that as you go out literally in distance in meters, you find the cross-linguistic word correlation also decreases in this linear fashion. And so here I can even just look at the most concrete words. So these are a set of words like that are naturalistic, that correspond to phenomena that would presumably exist in all of these contexts. Things like lake, star, sky, wind, cloud, fire, salt, night, day, right? So things that are universally experienced in a variety of different ways. Even these things, the correlation drops from roughly 0.6 to 0.3 over the space of e to the 7th meters, right? So the space of the antipodes, right, across the world, the farthest distance being in the opposite point of the globe. And we find furthermore that these are captured most by a variety of different kinds of grammatical, physical, climate, and lexical differences. So for example, if cultures are distant in their structure of kinship, that's the highest cultural predictor of the likelihood that the word associations will be the most similar. The same with the structure of law. That's also highly predictive of this. These are higher than, for example, even the climate distance, right, or the isotherm distance between places in terms of their relative likelihood of experience these phenomena. So here we can see that kinship is the highest cultural predictor, followed by possessions, followed by basic actions and technologies, followed by religious belief, which is almost 30% less influential, followed by law, followed by social and political relations, followed by emotions and value words, followed by the positions and value of domiciles, followed by the physical world, followed by agricultural and vegetative differences. But we find that there's a much greater predictor of the relative likelihood of alignment across languages, which predicts about twice as much as this concrete versus abstract association. And this is that within clusters, and when I say clusters, I mean domains of meaning. So, for example, within the space of musical instruments, guitar, solo, song, composer, all these things are going to be close in one language means that they're much more likely to be close in another language, right? That spiritual words, that war-related words, that health and healthcare-related words are going to be conserved in Arabic and Telugu and Dutch and English, but that the associations between those clusters are highly variable. And so we show that this is a much more powerful description of the semantic structure of languages, which means, for example, that when I prompt you with an essay in the context of the TOEFL exam, some of you have presumably taken this exam. These are 200-word essays in response to a simple prompt, that you're much more likely to have metaphors available to you, cognitively available to you as a function of the proximity of these meaning clusters in your language, which allows us to go back and predict the relative likelihood that you come from one language culture or another as a function of your deployment of those metaphors in context, which has, I would say, deep implications for the impossibility of translation on the one hand, but also the kind of the deep contextualization of language learning, right? So typically in language learning, we, after we've taught syntax, how do we teach deep semantics? We throw students at the literature from a language from a year or two, rather than showing the specific space of cultural associations within that language, which this analysis makes possible. And we can see basically these are the relative associations that are true across all languages and then only across specific languages. So, for example, there's a deep association between injustice in chemicals that exists only in Chinese, right? Between animals and sociocultural environments only in Bengali. But the association between competition and time is universal across all languages. I could spend a long time with these associations, but I'll leave it at that. The second analysis of kind of language cultures that I'll do just as a suggestion that large language models have facilitated is really is how to think about the relative density of the embedding spaces themselves and what that says about the structure of human communication on the one hand, and really kind of cultural and meaning transfer. So I'll be looking at these spaces in terms of their properties, not their positions in space, but their relative density as a way of understanding and predicting the rate and the character of cultural communication. So one of the things that we know from studying languages in general is Zipf's law, this idea that there are few words that are used many times and many words that are used just a few times. And so this phenomena called polysemy, that a single word can mean different things in different contexts, is actually variable across the entire language. So there's some languages which are systematically more densely packed, which is to say more ambiguous. You're using the same words to mean different things. So here we've got this example between English. I play soccer, Monopoly, and violin. And in Spanish, you can't use, there's no single word that links all these things. Yo juego fútbol y Monopoly y toco a violin, right? So those are two different words. And so we see that there are fewer bits in the English language, which corresponds to a generalized polysemy or reuse of words across that context, as opposed to the Spanish context. So we've got a more expansive conceptual space of distinct conceptual units versus a more compressed conceptual space in the context of the English language context. And my gentle timer just went off, so I'm going to race to the finish here. I'll conclude with a few ideas so that I really leave the bulk of this remaining hour for discussion. So then we analyze parallel corpora across these languages, right? So the Bible, for example, right? The New Testament, the full Bible, the European Central Bank, European Medicines Agency, European Union Bookshop, right? European legislative documents, which are again translated into multiple languages. In that case, in the order of 20, we've got various Unix documents, which are translated in up to 50 plus languages, news, subtitle corpora, TED Talks, crowdsourced sentence translation, and UN nations documents. Each of these correspond to a wide variety of language families. And so the idea is in these contexts, we've got the same content, the same semantic content, but they're translated into two different language contexts. There are many measures that you could assess the relative density here. One would just be the number of words, right, in the language conditional on context. And it turns out that corresponds to the Huffman coding, which is what we do. It's just a compression algorithm, which suggests how much information each token in word in this context is representing. And what we show, for example, this is a wide distribution across the world's languages in this information density that vary around the world.
Can I ask a question?
Oh, yeah, of course.
Can you go back 2 slides?
Yes.
So if you look at the plot at the lower left, it looks like fundamentalist Christians are right that they fear bookshops movie subtitles and TED Talks. Like, how do we deal with this plot that there's, you know, there's a few not so strong correlations which sort of like make sense, but then there is like how do we read this? Like this looks like, oh, it's like, okay, they're all related.
No. So I'm sorry. So this basically is just saying, what's the correlation, right?
Yes.
Between the, but like within the, so the idea is these are parallel corpora, and we're showing that there's a strong signal about the association between the embeddings across languages, conditional on context. So this is just validating the fact that, I mean, the reason these are weaker correlations, those are only in cases where the corpora are much smaller.
Okay, yeah. Okay, got it.
Yeah.
Yes.
So this is just kind of a data validation. Yeah, no problem. And so, but you'll see why it's critical that we're basically holding really constant that the content, because the whole point is how much meaning we're compressing into these various documents. And we find that if we take, for example, the pairwise distance between any two words inside of a space, and we average that across all the words in the language, that corresponds at about 0.8, so about 80% correlation, or 0.8 correlation with this language information density. So what this means, what a high level of encoding means, also means that that word is close to every other word in the language. So it really is a compression of the linguistic space in a way that has a deep geometric association and levels off, right? So we see this somewhat nonlinear association across almost all of the language context that we observe here. And most of the popular languages lie in the center of this cluster, but there's still a variance that's explainable there. And we find is that informationally denser languages that pack information into fewer bits communicate much more quickly. So more ambiguous languages, people speak almost twice as fast than informationally sparser languages, where they have to re-specify specific context-dependent tokens to describe anything in particular. But the conversations and expository documents like Wikipedia articles, where they're informationally dense languages as the medium of those conversations, remain much more focused and collectively compute over the same topics for more time over time, right? So even though you can imagine, for example, that a dense language, right, is just going to zing between meanings, it turns out that that's a multi-layer density, which means that it's much more likely, even if you do a random walk of associations on the semantic spaces, for conversations to come back to the same ideas over and over again. And the same is true for empirical conversations that we observe in context. And so this is Wikipedia articles. These are actual conversations. I could show you another figure that's simulated conversations, which has exactly the same phenomena, which suggests the conversations really are very similar to a random walk over these semantic spaces between individuals. And we find that these are not accounted for by other linguistic variables. I mean, it's the association with informativity, which is the amount of explicit and obligatory distinctions within the language, is like a negative 0.04 correlation. Fusion, which captures the degree to which a language relies on phonologically bound markers, is 0.24. The composition measure of complexity, or composite measure of complexity, is 0.11. So this is accounting for on the order of 0.6, 0.7 versus these linguistic variations. So these measures sum up about 120 different other componential linguistic measures. And semantic density, which is captured by these large language models, is a dimension that's effectively invisible to these classic dimensions. And that it corresponds with a number of other interesting cultural variables. For example, Hofstede talks about the power distance, individualism and collectivism, uncertainty avoidance, indulgence versus restraint. Schwartz talks about intellectual autonomy, effective autonomy, hierarchy, egalitarianism, et cetera. And we find is that a deep correlation between these language density assessments and some of these cultural variables. So for example, we find with this Huffman encoding, this information density, a strong correlation between things like the relative autonomy of a society and its density, right? Or the individuality and the density of a language, which is on par with the highest linguistic assessments, suggesting a deep cultural association between these information density, the ways in which they shape conversation, and cultural assessments. Okay, so all these different models where we're modeling individuals, we're modeling language units, facilitates also the ability to model social phenomena, right? Conversations between individuals. So we're simulating couples and dating scenarios. We're simulating conversations and conferences that haven't happened, that couldn't happen. And for example, we're engaging in things where we're predicting conflict and its content and character, where we're predicting collaboration and its content and character. I have to the left a beautiful paper by Michael Bernstein's collective group, in which they really just build rich simulations of individuals in collective context, and we're using those to build realistic simulations in the context of specific interactions. So this shows, for example, the prediction of conflict, that models like GPT-3, which have a really decidedly powerful superego, so they've been trained to be nice, or have a really poor performance if you're trying to predict conflict. You need a model that you can basically pull out the likelihood, basically, of toxicity and of conflict between individuals. So one has to think carefully about the models that you're using, either designing your own or using lighter weight models that don't have the same social and cultural engineering. Another thing that we've done is, this is with Junsol Kim, who I mentioned earlier. We've basically been doing misinformation identification, where if you were to look at online and see the individual taggers of misinformation to posters in the sphere of Twitter and social media, if individual taggers basically, cite, let's say, a PolitiFact or another basically news-based information source, a kind of a source check, and you post it against someone who posts, that's going to have, it turns out, we assess here, a negative reaction. It's going to cause individuals who are so tagged to retreat into information bubbles, even though that kind of misinformation tagging was intended to have the opposite consequence. Collective misinformation tagging, where you assess from a variety of positions the relative value or utility of that source, triggers the revelation of the misinformation tag to the poster, have a much more gentle effect, as I can show here. You can see individual misinformation tagging really causes people to retreat in their political diversity and the content diversity that they're exploring, versus the collective context, which has a far smaller impact. So we can do things like simulate those perspectives, but rather than waiting 6 to 7 days, which is how long it takes for birdwatch or community opinions, which is the label of this in the context of Twitter, we can do it immediately by building basically a kind of a tweet fact check perspective that assesses the relative likelihood that any particular assessment is helpful or not helpful. And this actually reveals a deep association, a deep property of these large language models. So for example, if I were to take just a plain vanilla GPT out of the box, and I were to ask it whether or not a particular piece of political information is true or false, I do much better. I jump from 0.5 to 0.8 or above 0.8. If I just, if I basically simulate a crowd of Republicans and Democrats, or of diverse political opinions, I get actually the lion's share of that distance closer, actually just by jumping near the the contextual question as a whole. So if I just say, hey, you're a conservative or you're a liberal, I get much closer in that large cultural space such that I have a better incidence against the hyperplane that separates a truth from a falsity. And the same is true for scientific contexts, where I can basically predict the relative likelihood that something is a true or false physics fact just by saying that someone is an electrical engineer or that someone is a mathematician, right? Where they have a closer incidence. Again, suggesting the power of these latent geometries of perspective. And I'll just suggest the potential that you can identify individuals within these spaces as vectors within a space, or of clouds of vectors. You can think of them as kind of entanglements of their different experiences. You can also make them entire vector spaces, right? So I can basically fine tune a model. That's what this left idea is. These are basically built for the purpose of just improving these models. If I fine tune a language model to produce toxicity, I can subtract that fine tuned model to produce a model without toxicity, and for which the probabilistic pathways into toxicity are very difficult to traverse as a function of this improbability. I can do the same for individuals. So I can basically fine tune an entire vector space model to kind of capture one person's perspective, another person's perspective, and now we're exploring the idea of producing operations on those fine-tuned vector space models that allow us to predict the entire distribution of conversational outcomes between those individuals. It's like the way in which PageRank, for example, simulated the network traffic that occurs at each node, that is the sum of many, many random walks across the space. So can we analytically basically produce these cultural and social outcomes from models? So this is work that we're doing right now in context. I'll just suggest the importance of being able to simulate these perspectives will allow us to do things like simulate global scientific futures and national scientific innovations and positions. This is work that I've been doing in the context of this Critical Technologies Network, where we're predicting who's discovering what, where, and when, in ways that correspond with broader work in the context of, for example, chronological modeling. So how can you use, for example, the idea of curriculum training, where you train a model on prerequisites and then more advanced topics? Can you turn this around in time to facilitate basically the prediction of futures as a function of past expressions in words? So I recently received a relatively large grant to build a team working with the Allen Institute for Artificial Intelligence, which is one of the reasons why I'm here in Seattle this weekend, or the beginning of this week, is to really use these to predict scientific futures in a precise way. And this also kind of pushes us to, how can we build, learn lessons from this diversity to produce not only human level diversity, but diversity that exists beyond the human level. And so my time is really beyond up. So I'm just going to whip through these last few ideas. Anyway, so we're, how can we build basically the least human artificial intelligences that really take seriously this idea of diversity? And I'll just mention the reason why this is relevant. This is a series of papers that I produced recently that basically show that the least probable innovations in the scientific space, so the ones that are the least predictable under this most predictive model, end up being basically produced by the most unusual people and combinations of people with diverse cultural experiences, really combinations of aliens or outsiders to a particular scientific area. And we take this seriously in the context of this final project that I'll just allude to, where we basically take a large language model that's encoded the scientific literature, and we build a digital double where we're really predicting all of the discoveries that individuals will make by, instead of encoding the language itself, we encode random walks through the hypergraph of the language. So we jump from a property to paper with a property to a person on the paper to a paper by the person to a material on the paper to a paper with the material. We run, 100 of those steps in the walk, tens of millions of times, and then we encode those walks to capture the relative cognitive availability of any inference that a material on one side of that chain will have a property of the other side. And when we embed those with the same language models that we might embed language itself, we improve our predictions by 100 to 500%. And moreover, we can show that we can predict about 45% of the particular people who will make any one of those discoveries that lie atop these ridges of human density in the semantic space. So we can use this to basically flip around the project, and instead of predict the most human-like associations, the least human-like associations. We can generate novel collaborations that don't exist. And what we find is systematically, by avoiding scientists, we're basically diving into the valleys in that human density space. So these are predictions that no particular person could make because the system of human education doesn't produce people like that. Not only are they very different from human predictions, and that if humans predict them, it will be years or decades into the future, but they're better on average, suggesting there's a diminishing margin of returns to theory. I mean, we're much more likely as a human scientific system to squeeze out the last drop from a particular theory than to jump to a new theory that would have many more low-hanging fruits in the system. This is across hundreds of diseases for which we're repurposing drugs, and many energy relevant, both for storage and generation material properties. I'm not going to say more other than just that one can basically put the entire scientific and cultural and social scientific system into a robot, as it were, using this active learning cycle and explore its possible outcomes. And this is something that we've done in the context of research on teams. This is an example of basically how it is that this robot can produce, through a kind of a computational theorization, computational phenomenology, where they select the optimal next experiments, and then staging actual human experiments, we can discover basically theory at scale through harvesting, in this case, an entire scientific system in the context of this digital double. And it turns out, these findings, these predictions that are produced by the system hold in our kind of pre-registered tasks. I'm just going to jump to a final wacky example where we basically just try to generate human diversity by actually just facilitating or creating a cocktail party. This is led by Xiang Lai, a student in my group, where LLM agents chat with each other across the space. They select individuals, other LLM individuals to chat with. And over time, they basically become much more clustered. They basically self-train each other. And in fact, the languages are like pigeons. I mean, it's not even English. It's like English with Chinese and Cyrillic characters. I mean, they basically become very different subjective and clustered groups inside these spaces. And we find when we harvest this inhuman diversity, I mean, human-like process to produce inhuman-like diversity, that these simulated societies have really powerful robustness properties. They're much less likely, for example, to be hacked by a kind of a poisoned, greedy, or a toxic agent in these spaces. Moreover, if we use and harvest the diversity from these simulated societies, we end up producing much higher performance levels on creativity tasks and tasks that involve and benefit from diversities of perspectives. All this to say is we're really trying to kind of produce a rich, complex system of human knowledge and culture through these contexts, and using them to facilitate and generate, richer collective consciousness. Now, collective consciousness is not just the classic consciousness, but the idea of, can we build self-models, other world models that facilitate causal prediction of how it is that individuals will respond to other individuals? Can we build theory of minds in these contexts? And there's certainly limitations, but there are a number of cases in which we're trying to improve these models to facilitate these associations. And this is a series of activities that I engaged with in the last couple of weeks with colleagues at Google, at Zhipu AI, which is an LLM company in China, and with the Allen Institute for AI here in Seattle, to kind of explore how to build richer cognitive agents in the context of these research spaces. And we're using many of these to actually improve large language models and deep neural networks themselves by taking social intuitions like, Heider-based balance theory into the improvement of the cycle of learning within these neural networks. I'm happy to chat in discussion more about this. But the conclusion is really that through these systems, we can understand cultural systems more deeply, and that we can control the emergent systems of AI and provoke human collectives culturally through generating diverse intelligence collectives. I'll just suggest, that at least to me, this has had not only a technological impact, but also a specific humanistic one that suggests the importance of conserving human diversity, but also cultivating algorithmic diversity to facilitate the designing of collective diversities that sustain cultural innovation of a variety of different types, and that really respect the properties of difference through kind of sustainable bridging rather than kind of universal bridging. So there are a lot of friends from the research lab and beyond that have been helpful and collaborative in this project. I'm going to close now. I'll stop my sharing and open our last 35, 40 minutes for discussion. Thanks for listening.
Mind's blown. Thank you very much. This was amazing. There's a question from the audience, which is Mikhail Tam.
Yeah, well, basically, it felt more or less like, I don't know, 7 talks together. So basically, I tried to note my questions, and they have roughly 7, I would say. But the question number 1 is...
I'm going to get my notebook out so I can keep track of...
Let's start with 1 and do a round, okay?
Yeah. I'm not going to ask all of them at once. So I will probably start with the first and probably the most simple and natural one. Can you provide us with the references of the papers?
Yes.
Yeah.
So I will.
But for example, I would be very curious about the language density story, or this the one on misinformation identification on ChatGPT, and then etc. So it will be great to have the list.
I will. I mean, some of these papers are, this is fresh. It's so fresh. So some of these are published papers within the last year. All these are papers that have been published, within the last year, or, several of them are on archive, and there are a few that are, I have figures, period. So I'll share all that I have, but yes.
Okay. So I probably will give time to other people, but
Okay.
reserve the chance.
Okay. Yes.
Something more.
Yana Sachi.
Okay.
Hi, thank you, James. Great talk, really inspiring. As someone who is studying self-representation online, and we, of course, see proliferation of bots and everything, and the fake news and the deep fakes, I'm really curious about the generation of personas, as you mentioned, basically extracting them from large language models. My question is, how do we validate the validity of these personas?
Yeah, it's a great question. I think in our particular case, we've been taking a collective approach in general, and an individual approach. So the collective approach is, to what degree, can we predict, for example, the distribution of responses, by a simulated population of Democrats, of Republicans, or of systems of Democrats and Republicans that correspond to the distribution of particular opinions of those persons. We've also been in the context of both cultural production and scientific production more broadly, predicting like who's going to discover what where.
Mhm.
Like, can I predict what country is going to discover this? Can I predict what person is going to discover this? So in the same way, I'm kind of taking a page out of the large language model, strategy, which is like, okay, can I mask a future event? And can I also do pre-registered events, where I basically predict that this is going to happen, and then I watch the world unfold and I assess whether those specific predictions are accurate. In other cases, for example, the conflict prediction, we're looking at Reddit. So we have Reddit conversations which either erupt in flames or continue to generate productive engagement. And so we just basically we do two things. I mean, we do the masking approach. So can we just hide some of these, train on some, predict on and assess on others, or I would say in a more serious way, can we basically look towards the future and do genuine predictions? So given the state of two individuals, where they're at, what their backgrounds are, can we predict the likelihood of conflict? And I should say the reason we care about that is because, I would say most of the research in the space is like very corporate. It's like, oh, hey, we're trying to minimize conflict online. We're trying to validate that there are useful, legitimate conflicts when people have different values. So I think, I think this is our typical approach of basically prediction, input-output prediction.
Yeah, I guess one of the reasons is as I work a little bit with prompting for copilots, sometimes it just seems like it's a self-fulfilling prophecy in a sense.
Same
So
word. I can imagine 2 or 3 meanings of that, which are mutually exclusive.
exactly.
Yeah.
So I'm thinking, is there a good way to also avoid that and be more precise in this persona manufacturing in a sense?
Yeah, that's a great question. I mean, so typically we begin with hindcasting. So we're predicting the past from the deeper past.
Mm-hmm.
But the problem with this is chronological modeling. So it turns out there are a number of things that make it difficult to build old models. And that's typically because old models rely on old data, and old data is the worst, right? And so, building like an evolving model that learns all the new stuff that begins with the earliest stuff is a disaster because so we're doing a whole bunch of weird things, like we're trying to you need the web to build a large, to build it like a 70 billion plus parameter model. You need the web. There's not enough text and articles to learn natural English, right? But then we have to date the web, right? Because yes, there's a date on access, but it's not when the idea emerged. And so there's all kinds of engineering that go into building a rich, in this case, like culturally contextualized, a particular time and place digital double that allows us to not contaminate the future. So a bunch of people, for example, will do things like, I've seen papers where they take a large language model that's trained on all kinds of unspecified data, and then they fine tune it to the past and they use it to predict the future, which is terrible. It like makes the actual future way more probable than other equal probable futures from the perspective of the past. So yeah, there's all kinds of like, care we need to take to deploy these models for real cultural science that don't predispose to self, predict the future. Absolutely. And I think, yeah, we need to be really careful with that.
At the same time, a little note about the cultural importance of these artifacts, say the Wall Street bets event. Like if we train the model on Wall Street bets, or it is at least included and we extract the persona from that, it is an important persona for the context of what happened a couple of years ago.
Yes,
even though it's massively biased and we cannot use it to predict the future.
That's right. So I think that's I mean, at least for me, the question is like, can we, if we're, so what the beauty of these models are that they're trying to capture and are effectively approaching capture of kind of connecting really distal, which is to say kind of like distant cultural influences and potential cultural interactions. Now, what we want to like put a block on is making it possible for, these models to basically entangle with the future in predicting the future. So if they entangle with like the future on the web and predict the future in science, then it's a charade. I mean, we're predicting the future with the future in a different domain, because both were influenced by the past. So I think we need to be really conceptually careful in doing cultural science, that we're doing what we say that we're doing. There's the potential in the mess of these models and the mess of their training to do exactly what you say, is to produce self-fulfilling prophecies that appear magical, that appear like they're cultural science. Whereas, at least from my perspective, I think a key part of this is conceptual and theoretical, which is, we need to highlight when these models should fail. Like they're failing when they should fail. So when cultural, for example, interventions, right, or surprises occur, kind of black swan events occur in culture. Things do things that they don't expect. That happens. It happens all the time. That corresponds to the most important cultural events in science and technology I showed here. I mean, the things that are the most surprising are systematically attended to disproportionately in these systems. So we need to basically harvest and realize the power of these models is when they're wrong, which is to say, that they can actually capture and identify, the surprise that occurred in a particular moment. I think when we realize that, then all of a sudden, these models become more powerful as digital doubles when they're right and when they're wrong, but no, it's a great question. And then these aren't perfect models. I mean, they're just much richer contextual models than we've had before, from my perspective.
Thank you so much.
I have a follow-up question. Thank you very much. So NVIDIA brought out this new sort of GPU generation last week, or announced it, where basically in a sort of fridge-like size box, you would have a backbone that can push the same bandwidth as the whole internet. Okay, so basically you can take your game to the extreme and sort of simulate the web. Obviously, if multiple of those, you can simulate multiple of those, and probably 1, 2, 3 years down the road, we can do this multi-way, basically. So at that moment, we can solve the manifold, right? We can actually find all the cracks that you say you can identify. We can play the random game that, sort of Donald Trump plays in real time, saying everything that can be said. But there's two things which we are stuck with. One is, this costs an incredible amount of energy to do, which is probably not very smart or intelligent. And number two is, how about the things that are outside of the manifold? Like, finding cracks that science doesn't bring these people forward because, it's for example, it's highly improbable to study art history and physics, right? So we need your model to actually find that crack. So I will be slower as a human than you will be as a computer. But there are other things that are outside the manifold. And so how do we take care of those? Like because the moment you identify that a computer is surprised, it may actually be too late. Like if the computer is just as surprised as we are, yeah, the model is as good as we are, maybe even better, but it still happened. And the stuff that we are surprised by may be bad. Like, a meteor hitting Earth, which we didn't see, an asteroid, right? Because I don't know, the possible inventions that are following from what we have done the last 6,500 years, according to our analyses, don't lend themselves to predict the kind of device we need in order to see the asteroid. So how do we how can we go beyond that kind of thing?
Yeah.
Can we find gaps that are outside the system, basically?
So, okay, so I will note that your question is impossible because the first half negates the second half.
Okay.
So, right, I mean, you're basically saying, hey, is it intelligent, to build all these models, and then the second is, we need bigger models, right? So, I will say, in the first half, I think, is it smart to build these models? I would say it's the definition of intelligence to predict the future. I think, like the ability of individuals to predict, theory of mind, how other people are reacting, like, the world that I'm facing, like this is the definition of intelligence. I think that any definition of intelligence incurs this as a backbone. So when we have really valuable things, I think that you're highlighting here, then it's exactly incumbent on us to try to anticipate the future. And we're going to do it either, by, putting 5 people in a room and, brainstorming on a whiteboard and making decisions, or we're going to do it by using the best cultural and social science that we can. So I think that, yeah, there will be frivolous uses for this computation. But I think, as you suggest at the end of your question, the second half of your question, there will be valuable uses for these questions. And so I actually think that, I think this actually begins to repair, in some ways, the massive imbalance in attention that we pay to social and cultural phenomena, because these are the phenomena on which the stability of our societies rests. I mean, these are the existential phenomena, and the idea that we're spending enormous amounts of money and effort simulating, these particle phenomena, and that we're not doing the same for social phenomena that that are much more provably in the short, medium, and long term associated with human flourishing, I think is absurd. So I absolutely think that this is not a waste of money. It's much less of a waste of money than many other investments that we've made previously. And I think there will be spillovers of things we learn here that will affect our understanding of other systems. Okay, that's the first question. The second question is, how do we take into account things that are that are black swan events, that are improbable things, that require us to include things that are unlikely to interact within the model because they're unlikely to interact in the world. And I think, the answer is we need to simulate more and more of the world. I mean, I think this is, in fact, there's here, let me see. Well, I'll just describe it to you.
Okay.
So there's another project that we did where we tried to assess, where it is that individual sciences looked, for ideas in general, and humanities. I mean, all areas of scholarship and science, and basically we could see this kind of citational cascade that corresponded to the hierarchy of the sciences and humanities. That electrical engineering is more likely to look to physics than physics is to electrical engineering. Computer science is more likely to look to EE than it is, all the way down to the cultural science. It's like you can see, a hierarchy of attention, and it's reinforced, which is to say that when something downstream is cited in an upstream field, it's much more likely to represent a kind of an idea laundering, which is to say the people who cite that work are disproportionately less likely to cite the work on which it's built if it's in a downstream field. But it turns out that when things are cited downstream, they're disproportionately attention gathering within the upstream field. So it's like there is a bias. It's reinforced culturally across the scientific space when it's violated. And when it's successfully violated, it's disproportionately associated with an infusion of good ideas, right, which are associated with improvement. So the bias was ineffective. It actually decreased. It filtered information away from where it would most profitably have been spent. And we know that because the people who cite downstream are more likely to be at the same institutions of the people downstream and disproportionately married to people in those downstream fields, right? So it's truly random in this sense. And so I think, I couldn't agree with you more that it's like Well, what does that mean? I mean, it means that like when you least expect it, right? When you least expect, like the most important associations in these systems will be the most improbable ones, which mean we need to incorporate more and more spaces of association. So I spent, a week ago, about 10 days in China where we were building dreams. We basically were taking offline memories, like visual memories, and linking them with online memories and creating new associations that the models could kind of discover in the same way that we do with memory consolidation overnight, And so I think that's what's going to happen. And of course, there will be things that surprise that are outside the space of the models, and those will be unpredictable by the models, and so I think that's why we build better models, and we are getting better at like weather modeling. We're also getting better at culture modeling. So,
Thank you, Mike.
Yeah, well, basically, first to address what you just said, because I think I haven't understood one thing you said. You said that so if indeed there is sort of this bias of citing in one direction or the other, then clearly something which is able to overcome this bias must be, well, untypically good. But it doesn't mean to me that the bias in itself is counterproductive. So you just, the fact that things going upstream are particularly good is just because they're selected to be able to overcome biases.
No, Mike, I love the idea there. I love the idea, but I'm going to push back. So for example, if someone downstream is looking upstream, okay, then it doesn't matter where they are, because everyone downstream is gazing upstream. Like everyone is living that hierarchy. Okay. When the people upstream find something downstream that's useful, so you're saying, hey, it's just that those downstream things get selected into, then why would it only be the people who happen to be at the same institution as the particular other person, or they happen to be married to that other person, that like those are the only good things. The only good things are things that happen to
That's your point.
That's totally implausible. So right now we're basically setting as a set of experiments, a bunch of conversations and conferences that will try to validate that perspective by showing that it's not just a selection effect. But I think it's implausible that it's predominantly a selection effect.
Yeah, and, well, basically, I wanted to ask a couple of questions which are sort of
One first, then
okay. So let it be one first. Okay, let it be this one. Concerning all this sort of language density, information context, and languages seem to be very, very different in terms of how much language forms they have. For example,
how much language what?
Russian, or for example, Estonian has a lot of flexes, while Chinese and English do not have it. For example, I mean, adjective in English is one word, adjective in Russian normally has 18 at least. Oh, no, not in 1824, sorry. So how you treat this topic of what is a word, what is the unit of the study here?
Yeah, that's a great question. Yeah, I think that I mean we're taking baby steps here. So we're using standard tokenizations across these languages, but absolutely, like in German, for example, you're going to get a composite word, that includes effectively the adjective, sometimes verb conjugation, noun, I mean, so all those things we're going to. I will say, we take two approaches. One is we take the native tokenization approach within any particular language. And the second approach is we basically just slice things up into morphemes, and so we fragment them. And now what you're suggesting is that even if we fragment them, they basically are like, they have greater interactions in one language than another that we're kind of ignoring across these contexts. And I think that is a fear. I think that's a legitimate.
How much is the result dependent on whether you choose this first approach when you take sort of native?
For the second study, very little. For the second study, very little. So these so the second study where I'm talking about the relative information density in these contexts, this looks highly robust. So for example, I can build an information density by letter that shows the same phenomena, as by morpheme, as by word. It's slightly weaker the smaller you get, but it's still strongly present when I look at the letter itself, all the way up to the full complex token. I would say we didn't do the same robustness check in the first study, but we had far fewer. The second study had 1,000 languages. The first study only had 36 languages because we only had, that's how many, we languages for which we had a density of TOEFL essays, basically, that was large enough to do the modeling. So I think there's many more things to do in this space. These are like baby steps, but I'm kind of excited by the possibility. And now I think the work becomes to really take into account lots of subtle linguistic and cultural differences that are beyond the scope of our first baby steps.
Super cool. Mark Metz.
Thank you. That's all very exciting. So I have one very not really profound question at all, actually, and then a bit larger one. Small one. It's actually about this TOEFL study about the Wikipedia articles. I understood. So what was there was some measure about how you compare these languages was with the cosine distance, like within and between. Like this, could you tell a little bit about it?
Yeah, sure. So
this was the part kind of.
Yeah, so we're just taking pairs. So you can think of pairs of words, So every pair of words has a you can think of them as if I locate these two words in one language context, I can look at how close they are, in English language Wikipedia, in Estonian Wikipedia, and in Swedish Wikipedia, in Russian Wikipedia. I can also look at their proximity in English language essays that are written by native English language speakers and by native Swedish speakers and by native Russian speakers. And so we're really performing an identical analysis across those two contexts, right? Where people are performing passable English language essays, so non-erroneous essays that are written by people with the same native language context. And then we're seeing the degree to which those conceptual relations, and by relations, we're just assessing them exactly as you say, as the cosine distance between those two words in those two models, the TOEFL model for Arabic speakers writing English and the TOEFL model for Wikipedia articles written in Arabic, right? And then we assess for both of those cases the relations between those words and those pairs of words in every other language. And initially, are kind of, we take from the literature, is that this assessment that basically concrete things are going to be constant across, and they're going to be diverse. Abstract words are going to be diverse kind of across languages. And we find that that's true, but concrete words are also highly diverse. That was my point. Even the most concrete words that every language culture has access to are highly diverse. And then we found that a much greater conservation was when we cluster the space. If we just build a clustering, and it really doesn't matter what clustering, you build. I mean, we built many alternative clusterings. They all produced approximately the same finding, which is that basically, if two words are within a semantic cluster, you know, like within healthcare, within music, you know, within the religious world, et cetera, that they're going to be, if they're close in one language, they're going to be close in another language. But if they're across these clusters, that they are potentially, you know, they're much less likely to be close across languages. So basically, you know, like in Chinese, for example, languages associated with family are close to one another, like they are everywhere. Languages associated with like mountains, lakes, and natural phenomena are close to each other in Chinese as they are everywhere. But in China, those two clusters are right next to each other. So if I ask you a TOEFL essay about your family or about the way in which families take care of aging grandparents, then it's almost inevitable that you're going to use a mountain-like metaphor to describe that language in a way that would be implausible in Telugu, right? Or in some other language cultures. And the reason we're doing cosine distance is just because as you go up in dimensions, you know, a hypersphere, the surface of the sphere grows to infinity as the volume grows to zero. So basically a high dimensional hypersphere looks like a spiky ball. So at some point, everything lives on the surface, which is why Euclidean distance is a terrible idea. It's like drawing a chord through a circle, right? You're not like moving along the surface of meaning. So here, that's why we take a cosine approach, which is not so dissimilar from a kind of inner product approach.
Isn't the cosine distance also, I mean, it's less problematic than the Euclidean distance, but still problematic, isn't it? Because why would you, like, what gives us the assurance that the geometry on the projection is actually sort of preserving the angles? Like, for example, if you bet two different languages, are the differences you get between languages due to the differences in the language, or are they due to some artifact of the projection? Because, you know, angles just change if whatever your bet is a little different.
Oh, right. But this is why we're only looking at the distance between any pair of words inside the space. So we don't assume any cardinality, you know.
But are we okay to assume that the space is Euclidean?
Yeah. So okay, that's a great question. In other work, we show that because it's a deep question. So because we show, you know, so for example, social networks are often hierarchical. Language networks, because of Zipf's law, are also hierarchical, right? And
but they're much more dense because they're basically, particularly you're starting with a
they're also
classification.
much more hierarchical, though.
Is that true though? I'm not sure. Like you have you start with a classification network, right? So you got verbs and you got contexts, and that is by necessity dense, likely, low diameter. So clustering is a nightmare because you may end up with this sort of
that's my whole point. I mean, clustering doesn't make. I mean, so clustering assumes like local density within and separation between. That's like the definition of clustering. And I think the point that Mike was making is that which is an excellent point, is that if you have things like hierarchy in the space, then a hyperbolic space, which is to say a negatively curved space, is going to give a better representation than a Euclidean space. And it's true that you basically require 2 orders of magnitude fewer dimensions to represent hierarchical systems like language or social networks in even a naively like -1 curvature space, you know, which is to say hyperbolic space. So absolutely, you know, we are, for many of our language models, basically, when we care about not just the distances, but when we really care about the structure of the hierarchy, then we're doing exactly what you say. We're trying to estimate the right geometry because we care about that representation as a kind of a theory. And so, yeah, so I couldn't agree more. The challenge is, you know, we have, you know, since Einstein, for example, like a well-formedness to how to think about like curved space-time as a function of a density of points. We don't have that for a network of points. And so I'm actually super interested and I'm launching some intellectual activities to build some, deep theory that basically allows us to estimate the continuously changing curved positively, negatively. So a system that has clustering, as you say, is a positively curved system. It means that any random walk in the space is likely to return to that initial point. A negatively curved space is like has a bunch of ridge points. It means it's much less likely to return than at random. And of course, the parallel line hypothesis, or the postulate, the fifth postulate in Euclid's geometry is basically means that do we have dimensions. So I think, yeah, so I think like getting the right geometry is important if we care about these representations as theories, and sometimes we do, we don't always. It doesn't actually matter with prediction because we can use flabby Euclidean dimensions to make the same predictions. But I think estimating these shapes is for those of us like you, who care about the structure of culture, I think that's a really exciting opportunity.
Yes, I have a sort of like I have me smiling is not like ridiculing anybody. This is the same kind of smile I have when I stand in a chute or in a forest with deep powder snow, and I'm excited by the challenge because I think there is a really huge rabbit hole in front of us, which is
only one.
And I think I have a sort of long-term bet going on, which is a preprint I put out in 2019 called Cultural Analysis Cetus, which tries to sort of like bring evidence that sort of network science, higher order topology via Poincaré, and sort of cultural meaning spaces via Cassirer and Warburg, and also the computation of Shannon all go back to the same couple of lines in Leibniz. And if that is true,
wait! I need the lines. You can't just drop that bomb.
I will send it to you. I just mentioned it. So the notion is like, this is not me being brilliant or whatever. It's Ernst Cassirer basically saying that meaning, like the meaning function, is actually purely mathematical. What he means with that, it's a topology, it's geometry, and it's multidimensional. And he said that in 1929 or 1927. And so the interesting thing is this is all coming back to us, and it can increasingly not be denied. Like what you showed us today is, and I sort of say this to wrap up because we used our 2 hours. What you showed us today is that geometry, mathematics is the method of the future to actually look at meaning of words, of groups, of intentions, of cultural objects, and so on. And it just cannot be debated away because everybody who uses not even a large language model or neural network, but even a search engine, you sort of like admit that there's a mathematical structure below that. And that is sort of something which is at the same time wonderful because we can actually go beyond our, sort of human capability of being in a library. And like, there's still plenty of like, if you have the right strategy, you can find new things in the library. It's absolutely zero problem. In a single bookshop over a coffee, you can actually find things that no large language model will ever produce, but still this is incredibly powerful. But at the same time, and I think that is sort of like interesting in the light of things that people use this for good and bad. I mean, they use it to exploit the system, right? Like obviously what you outlined, like finding scientific ideas in the cracks where nobody looks, that looks like fracking of patents, obviously. Like people, somebody doing that, right? So now the key thing is, what is the bias, right? And so that at that moment, this notion of geometry is really, really important. And we really need to learn if you can use cosine distance or if it should be something else. Do we need a kind of other approach to this kind of geometry? Should people learn this in primary school? And so on. And there, I think there is a more shadowy side, which is if we do this wrong, like if we spend the energy of half the country and half of Earth to actually calculate things which are fundamentally wrong and then make decisions, legal decisions, decisions of peace and war, decisions of love and hate on these kind of calculations, then we better have our act together. And in the same way that, you know, everybody's reluctant to say power law whenever they see a straight line over several orders of magnitude, maybe in 10 years, people are super reluctant to say the word cosine distance when we look at these kind of systems, which are highly multidimensional and may not be linear whatsoever, may not be Euclidean whatsoever. So this angle does not make sense. And so that is, I think, a really, really interesting thing to think about. So at the same time, you showed this absolute wealth of really cool results, while at the same time you say, oh, this is really just a stepping stone. And I think that's the exciting part. There's really something going on which will give a lot of work to a lot of people for a really long time. So that is sort of something which is really exciting, that there is a new sort of like global renaissance of like, oh, let's understand art and culture and social systems in completely new ways. And it's not that the machine steals our work, because we really need to understand how that machine works. And that is sort of like the cool thing. So yeah, with that, I think I thank you very much for joining us at 6 a.m. from Seattle. And it's a great honor to have you in the Open Lab seminar while we're competing with the Allen Institute and Google. So thank you very much. This was great.
Yeah, it was my pleasure. Thank you for inviting me, and I'd love to meet your team in person sometime. I'm over in Europe frequently. So anyway,
Yes.
thanks for your
You're
engagement.
invited.
Great questions.
Bye-bye.
Okay. Goodbye all.
Bye.